Hello YouTube. Today we're going to have a tech talk about coupling capacitors. In my last video where we were working on the digital RF switch, we ran into an issue where we found a lot of our signal at the frequencies that we were working with. We were using 5 megahertz and 7 megahertz. Much of the signal going through was just disappearing, or what we call insertion loss. That's when we have a circuit or a device and you pass a signal in and the signal coming out has losses. We were looking at that, and when we went and looked at the data sheet, we found that the losses we were seeing was way higher than what the manufacturer listed in the data sheet and expected it to be. And because of this, we wanted to dig into that. And I had a theory on what it was, and it turned out that the coupling capacitors or DC block capacitors, same thing, on the inputs and the outputs were the problem. And so we went in and we changed the capacitors. If you haven't seen that video, you might want to go watch that before or after this video, either one. But we went in and changed these capacitors and resolved that issue and got this thing to run within specs at the frequencies we wanted it to use. So it was a choice made by the people that made the board and put the component on of the size capacitors they use. So what is a DC blocking or a coupling capacitor? That's what I want to talk about in this tech talk. I want to talk about what they are, why we use them, why the size matters. What they are is, to make it simple, I thought that I would create this little diagram of a two-stage audio amplifier, or RF amplifier, I should say. And I want to kind of show how coupling capacitors come into play and why we need them. We're also going to go in, the second part of this is going to be, how does capacitors block DC but allow AC? And then the third part, we'll do some practical, set up a little jig and show you different size capacitors and how they affect the signal. So in this little diagram, you can see that we have a signal coming in and we have a CC, coupling capacitor, at the beginning of our amplifier. We have another one in between the two stages, and then we have a third one on the output. They're also called, as I said, DC blocking capacitors, because that's what they do. When we have a signal, let's say we have a signal, let's ignore this one. Let's say a signal comes in and we have a signal, an AC signal coming in, and we're amplifying it in this stage. Well, to make an amplifier, we need to bias the transistor. We have to have a certain amount of current running through here. We have to have a certain resistor here. Typically, we've got a certain resistor here. And what happens is this bias all these biases get set for certain currents and voltages to get the signal to come out amplified at the rate we want to amplify. So we get our AC signal out of here, usually amplified, not always, but usually amplified through the first stage. But we also have, as you can see, we've got DC voltage here. We've got our VCC here. We've got DC voltage at this point. And the problem with that is, if we pass that on to our next stage, think about it, not only will the transistor be varied by the AC signal, but it'll be turned on continuously by that DC voltage. And so we will engage the transistor, it never turns off. So it stays on running all the time. So we get a couple things. One is, we're messing with our biases for this side. We end up with some distortion because of this DC coming in. We also end up with this transistor running hard, and that means it's probably going to run hot. We're probably going to look at an early failure of this transistor. So what do we do about it? Well, that's where your DC blocking capacitor, your coupling capacitor, comes in. We couple these stages through a capacitor, and through the magic of a capacitor, it will refuse to allow this DC signal from making it to this side. Only my AC signal will come through. That way, this stage never sees it. The two of them are isolated DC-wise from each other. This stage cannot affect this stage's DC characteristics. This stage cannot affect this stage DC characteristics. They can only pass the AC signal between them, and that's exactly what we want, and that's exactly why we use it. That's why you have one on the output, to isolate the second stage from whatever you hook the amplifier to. That's why you have one on the front end, because whatever's over here generating the signal, we don't want the DC characteristics of our amp being affected by it. We don't want to affect that section. Think of them as DC guards. They say, okay, no DC from you can come to my new stage. And this is what we use these for. Now, what we're going to get into now is, how does a capacitor block DC but allow AC? So I'm going to get set up and we're going to go through that. And again, the last part will be, we'll actually set up and show them doing that and what the sizes, how the sizes affect what signal comes through. So let me get set up for the second part. Okay, I've got set up a little test rig here. I think the first important thing to do is, before I try to explain to you why a capacitor blocks DC and allows AC through, think it's very important that we prove that's true to you. I've set up a little jig here. It's very simple. What I've got here is I've got a 10 microfarad capacitor in series with a 10 kilo ohm resistor. And I've got my DC power supply set up here, and I've got my oscilloscope set up on channel 1. And I'm currently looking at the input to the capacitor. So you have the input of the capacitor, runs through the capacitor, through the resistor to ground, back to your ground, and I've got my oscilloscope across ground and the input. So if I turn my power supply, I'll have to reach, turn my power supply on, we should see some voltage. And lo and behold, we do. We're getting 6 volts. So currently, the oscilloscope sees 6 volts at the input of the capacitor. Now, here's the question. Will we see 6 volts at the output of the capacitor? So let's pull this and move our, this is just the probe of the scope, over to the output of the capacitor. And notice we do not. We do not get our 6 volts through the capacitor. Our DC is being blocked. Let's go back and prove we do have our 6 volts on this side, but we don't, we're reading like 80 millivolts, but that's just noise on the bench here. But you know, if I go over and hook to ground, I'm still seeing 80 millivolts. That, I think, shows that we're not allowing that DC voltage through. It's a 10 kilo ohm resistor, so it's not hard to do the Ohm's law and show that we should be seeing some voltage across that. If it's blocking the DC, what about AC? Well, that's easy enough. Let me disconnect my DC power supply just to be sure. This is going to short the capacitor out. Let's make sure we short and there's nothing there, okay? And now let's take and input from my signal generator. I've got a 60 hertz 20 dBm signal that I'm going to put into the same circuit. Now we're back on the input. We're looking at the input of the capacitor. So let me turn on that signal, and lo and behold, we see a 60 hertz 6 volt signal coming in. Okay, so now the question is, do we see that on the output side of the capacitor? Well, yes, we do. But notice that the signal is attenuated dramatically. We have losses. We have insertion losses through that capacitor. It is not sending the full signal through. We're losing. Now, that's going to get into why a capacitor, the reason that's going to be has to do with how capacitors pass AC. So it's going to have to do with the size of the capacitor that's going to matter. So now we can build on why a capacitor does this, why the size of the capacitor makes a difference depending on the frequencies you're trying to pass. Let me reset up to continue on, and I'll be right back. Okay, let's talk about capacitors and why they won't pass DC, but they will pass AC. Okay, I'm going to kind of give you the simplistic hand-drawn idea, and then I'm going to go pull up a couple little images I created on the computer that I turned around and animated for you to kind of give you a more of a, I don't know, maybe a simpler way of looking at it. Capacitors are basically plates separated by some material, some dielectric in here. But while these are conductive, the dielectric isn't necessarily conductive. So you almost have to think of this as an open circuit. So if we send charges in from a battery, let's put a battery in here, and let's send a charge to the capacitor. Okay, that's going to be DC now. So if DC goes running into the capacitor, what's going to happen is, first you have to remember, electrons are not positive and negative when we talk about charges. Electrons are always negative. So when you talk of a positive charge, you're talking of a lack of electrons, basically. So one side of this plate is going to get a large amount of electrons packed into it. The other is going to have electrons. Remember, there were electrons on these plates before we applied charges. They're going to be neutral. That's why there's no voltage. This is a discharge capacitor. So to be neutral, that means the same amount of electrons have to be attached to this plate and this plate. So what happens when we put a battery, we motivate. That's what voltage is. We motivate these electrons. And when we motivate them, when we use an electromotive force, voltage, we cause these electrons to move from where they naturally want to be. We corral them. And that voltage corrals them and makes them move. When they move, that's what we call current. So we're going to get a current when we first put this battery on, because one side of the battery is going to pull electrons to it. The other is going to push electrons to the other side. So we're basically moving electrons from this plate to this plate, let's say. Okay. So what happens is you're going to get less here and more here. You're not really moving current. I know that's going to fire up some people. There's going to be a lot of theories come in. There's all these theories about current flowing through a capacitor temporarily, and it doesn't, and it does. But current does throw in a circuit with a capacitor when you first apply it, because these electrons move this way. They move this way. Because of that, current flows in the circuit. But technically speaking, other than leakage current, current doesn't flow from one plate to the other. So we hook up a battery and we see current appear to flow through this capacitor at first. But we're really just draining one side and packing it on the other side. Now, as this happens, as you build more electrons on one side and less on the other, you create a voltage in this capacitor. So the voltage climbs. And at some point, when these plates are at the same voltage as the supply, it will flatten out and be that voltage. There is current moving during this point. There will be no current from the point when it matches the battery voltage until it gets to forever. It will sit there, other than we're going to discount and remove leakage, any leakage in the capacitor. Let's imagine it's a perfect capacitor. You're going to have current flowing in this circuit as the voltage builds, as the electrons move and pack on this plate. Voltage is going to increase, and when it gets the electrons moved from here to where they're matched by the voltage of the battery, it's going to hit the battery voltage, and at that point it's going to stay there. No matter how long you leave the battery hooked up, the potential is there, but nothing will move at that point. It's going to stay static. So because of that, that means this DC cannot flow through this capacitor. We do not see DC going through a capacitor. We only see current when you first apply it to reorient the electrons on the plates. After that, the capacitor is charged, nothing flows through it. They didn't flow through it before. I want to be clear on that. There's going to be people that argue, and you can put it in my comments and go on, but no current flowed other than leakage current. No normal current flowed here. It just reduced electrons here, increased electrons here, moved them through the circuit. By all measurements, you will see current. It'll look like it's flowing through the capacitor, but it's not. Now, that's why DC current doesn't move through the plates of a capacitor. Think of them as an open. It's open in here. There's no way for the electrons to move. If we put a jumper wire across, then current would flow. Okay, with that done, that's DC. Why will it flow AC? Well, basically for the same reason. Let's think of it from an AC point of view. AC is going to do the same thing. Here's our plates. We're going to put an AC source on the plate. What's going to happen is, depending on which side we are on the AC cycle, electrons are either going to be moving in this plate or moving out of this plate. It's going to be the opposite for this plate. Just as we were pulling electrons in and out of the plates, and that gave us the appearance of current flow, so that it appeared current was flowing through the capacitor, but it wasn't. And just with the DC, and remember we're talking AC here, with the DC, it rises, the voltage across this capacitor rises up until it meets the supply and flattens out. The problem with this is in AC, you're not going to have that. The voltage is going to rise and then it's going to go down. This is 0, let's say. Voltage is going to go up, voltage is going to go down, voltage is going to go up, voltage is going to go down. So here's what happens. When the voltage starts going up, electrons flow one direction and pack on one plate and get pulled from this plate, and current appears to flow. But before the plate gets fully charged through the voltage of this signal, since it's varying, it's not at a fixed voltage, it continues to climb, so it continues to move more and more electrons until it hits the peak, at which time it reverses. What happens is we're going up on the wave. So here's your wave. Let me see if I can make sure I get it here. Here's your wave. We start going up. We're moving electrons, packing here, removing them from here, and we get to here, and all of a sudden we reverse and start going down. So the electrons here are more now than our signal. So they want to now start coming out this side, and the opposite on the other side. Electrons want to run back in. So they start running the other direction. So current is again flowing through here. And that goes on until we swap again down here. And all of a sudden the current starts flowing a different direction. And it gets up to here and it stops and starts flowing the other direction. So because of that, while the plate is not really truly conducting current through the capacitor per se, the appearance of current flowing through happens because by doing this, these increases and decreases of current flow lets you see across this capacitor the same signal as the electrons move. You're not flowing through the capacitor. Instead, what you're doing is pulling charges in and out of the plates, and that gives you the same signal across the capacitor as what's going in on this side. Because of that, we can take an AC signal and pull that AC signal out the other side. To kind of make it a little clearer, I've done a little animation. Let me pull up some videos here. Okay, and the video here you're looking at is a capacitor. We're looking at, this is DC, and it's equal charge on both sides. Think of it as a piston. This is a cylinder with a piston in the middle, and the little dots, the little circles or globes, they're your electrons. So if you start pushing power in one side, the piston will get moved to the other side and push those out the other side. So you have a positive and negative, start sending power in, pushes the piston to one side as the capacitor charges and fills with the electrons. But when it gets to the end of the travel and has pushed all of them out of the other side, it's done. Those electrons can't move through to the other side of the capacitor. Now think about it. As it started moving, so here we're in the middle, we start moving, we move a little more, we move a little more, we move, and we get to the end of the cylinder. While it was moving, electrons were leaving that side of the capacitor. So it sure looked like current was flowing. And current was flowing, but it wasn't flowing through the capacitor. It was flowing out of the capacitor. Once it gets to the end of that stroke of that cylinder, the capacitor is full. It can't take any more charge inside. You're done. Nothing's coming out the negative side of that capacitor. And so there's no way to flow current through that capacitor. There's no movement, no signal, no DC is going to come through at that point. So that's just as this is the cycle of charging the capacitor, and then bam, we're done. That's it. Now let's look at AC. AC, we start out in the middle. Let's bring in some electrons on one side, and the piston will move to the right. It will begin to push electrons out the right side of the cylinder as the piston moves to the left, as the electrons come in the left. But just as it does that, the current reverses. The signal reverses direction. So now the piston moves back to the middle, bringing electrons in on the right side and expelling them out on the left. It'll continue to do this. It'll now move to the left as it continues to bring electrons in. But notice it never gets to the end of the cylinder, because by the time it gets partially charged, our signal flip-flops again and we start back the other direction. So because of this, we can push electrons in and out of the capacitor continuously, matching what we're applying to the capacitor, and we can get that same signal that's alternating to flow right through the capacitor. As long as our signal is varying, our capacitor will duplicate that signal on the other side of it. So I hope that makes it a little clearer for you. Hopefully that clears up and can get a conceptualized vision of why capacitors block DC but allow AC. I'm sure there's a lot of holes that people can poke in the way I've described it. I'm trying to keep it, not get into the extreme quantum physics of capacitors, but this is basically why this functions the way it does. Let's get done with all this theory stuff. Let me get set up on the bench. I'll show you how the size of the capacitor has an effect on how efficiently it can pass a AC signal of different frequencies through. And if you think about what we're talking about here, you can kind of start conceptually seeing why. Imagine that our frequency is very, very low, but our piston and our cylinder is very, very small. Small little capacitor. We put a signal on, but before we change directions, that capacitor fills up. So it gets all the way to the end of the cylinder and it can't flow our signal. Then the signal turns around and it starts going back the other way. It goes all the way the other way and it stops again. So what happens is you do get in and out on the cylinder and you do get your signal, but it's greatly reduced. A lot less electrons are moving in and out of the capacitor than what would be if the capacitor was larger. Because if the capacitor is larger, it can handle more charge. Therefore, it won't charge up fast enough. It's much slower charging at a given voltage. So as you put your signal in, the capacitor never fills to one side. The piston never makes it all the way to one side before it switches. So there's really not a big loss of your electrons. You get all your electrons you put in out the other side, you get all the electrons the other way. When you put that small one there, you hit the edges, you charge up too fast, and you're losing electrons. So you do not get the output signal, you have losses. And so this is what happens. And let's get on the bench and we'll show you how much of a signal difference you get from different capacitors at a fixed frequency. So see you in a minute. Okay, we're back on the bench. I've got the same jig set up that we had earlier looking at the capacitor blocking DC. And now what I want to show you is how different capacitors have an effect on frequency. I've got my signal generator set up to 10 megahertz. I'm putting out 20 dBm. So I've got 4 capacitors. I've got a 10 microfarad, I've got a 68 picofarad, 33 picofarad, and a 10 picofarad. Let's look at what happens with our signal passing an AC signal through different capacitors. So I'm going to go ahead and plug in this 10 microfarad. You'll see we're getting 188, 190 millivolt peak to peak. If I move my scope over to the input, you'll see that that's basically what we're putting in. So that 10 microfarad capacitor is having almost no effect on the signal strength. But if I pull this out, remember it had almost no insertion loss through this capacitor. There was no losses, okay? I'm going to move down now to a 68 picofarad, and let's look at what happens. Okay, now I'm down to around 100 millivolts. So we've had a dramatic loss. The insertion loss has come up. We've got a much higher loss in our signal. So let's move from our 68 to our 33, and progressively this should get worse as we go. Okay, now we're down to about 56 millivolts, as you can see. So each time we go down in capacitance, our signal is being restricted more. So here is our 10 picofarad, and you can see we're only barely 24, 28 millivolts. We barely got a signal anymore. This is what was happening in that little module. The capacitors were much too low a capacitance, so they were blocking the frequencies. We had to increase the value to allow those lower frequencies to pass. They would have worked great at your higher frequencies. Above 500 megahertz, they would have been great. But unfortunately, we weren't working in that frequency range. So we had to change those capacitors to allow our signal to more freely pass through them. There's always losses, but if you go with a large enough capacitor value, your losses are going to drop dramatically and be almost unnoticeable, as with this 10 microfarad. Now, we know that 10 microfarad will block DC. I proved that earlier. We tested that and showed that DC will not pass through a 10 microfarad. So you're still going to block your DC current through this capacitor, but you're going to let pretty well all of your AC signal through. And if you think about our discussion on why capacitors pass AC and do not pass DC, you could see how a larger value capacitor can handle a slower change because it takes longer for the same voltage to charge it fully. So if it's not going to charge all the way up in time before the signal changes, it's going to let that whole signal move through. You go up to a small capacitor, what you run into is a slow changing signal has time to charge the capacitor all the way up, and it starts blocking the current through, and vice versa. So you get more restriction to your signal getting through. That's why the size of a capacitor has an impact in this one. Hey, I hope you learned something. I hope this was interesting. I hope to catch you in my next video.